This is a part 2 of simplifying radical expressions when division is involved. In all of these situations, we've maybe have something that's more familiar over here that we handled last chapter, something that we would have handled in Algebra 1, but it's been a little while, and then 2 new concepts that we haven't handled yet in Algebra 2. All right, so first of all, what we have to do when we deal with the square root of 2/3, we are going to try to break that apart first to see if there's anything that we can take the square root of. All right, the square root of 2 exists, it's just an irrational number. The square root of 3 exists, it's just an irrational number. We can find a decimal approximation, but not a decimal equivalent. So this is troublesome. When simplifying radicals, you are not allowed to have a radical in the denominator of a fraction, just like you're not allowed to have a fraction as the radicand in this expression. So, in order to simplify this, we are going to multiply by 1. Alright, and this is from last chapter, so this should be familiar. You guys know the gimmick here. Multiplying 1 doesn't change its value. We're going to get the same output. So we're not going to multiply by 1 written as 1. We're going to multiply by 1 written as the denominator over itself. The reason is this. When I multiply my numerator, I get the square root of 2 times the square root of 3 gives me the square root of 6. But when I multiply my denominator, I get the square root of 3 squared. And we all know that the square root of 3 squared is just 3. The power matches the index. There's a 2 here. It's a square root. We just don't write the 2. The power matches the index. Therefore, those counteract each other. You're left with the square root of 6 divided by 3. We do have a radical in a fraction, but it's the numerator of the fraction. That's okay. And our denominator is a rational number, so this is something that is considered a simplified radical. Over here, let's look at this from the standpoint of algebra, all right? So we've got an x in this case, the square root of 4 divided by x. We're going to rewrite that as the square root of 4 divided by the square root of x. The square root of 4 we can handle. We know that that's going to be 2. But the square root of x, that's not a perfect square, or we don't know if it is a perfect square. It might be 25, but we don't know if it's a perfect square, so that we could take its square root. We've got to assume, though, that it's not, all right? Because the square root of x, we don't know what that is. But we do know that the square root of x squared is x. So what we're going to do is rationalize the denominator in the same way we did here. We're going to multiply by 1. But 1 is going to look like the square root of the denominator over itself. The square root of, the square root of x over itself. The denominator over itself. This gives us 2 square roots of x over the square root of x squared. The square root of x squared is x. Now when we do this with square roots, this is actually kind of easy. It looks maybe a little bit complicated, and definitely the first time you saw it in Algebra 1 and in geometry again, it was complicated. But we're just multiplying by this thing over itself. All right, so we know what to multiply by, and then hopefully we don't mess up the algebra along the way. But we're able to arrive at an answer. This might not look more or less complicated than that, but this is considered a simplified radical expression. And because we have all the perfect squares are taken care of, there's no fraction under the radical, and there's no radical in the denominator. All right, so this is the way that this goes with square roots. Not too bad. But transitioning into cube roots or fourth roots or something along those lines, things get a little bit more dicey. When we take the cube root of 1/9, we're going to rewrite that as the cube root of 1, which is just 1, and the cube root of 9. All right, now 9 is a number that we're familiar with and that we're happy with when we're dealing with square roots. But when we're doing cube roots, we're going to have some issues. Because 9 is not a perfect cube, so we need to rationalize the denominator. The problem is we can't just multiply by the cube root of 9, because then we have the cube root of 81. And 81 is not a perfect cube. All right, so this is where our problem becomes a little bit more, the word I like to use is cumbersome. All right, it becomes a little bit more challenging to us. So let's go ahead and see. The cube root of 1 we know is 1. The cube root of 9, we're not sure yet, but we do know that 9 is a power of 3. So I'm going to rewrite this. You may not want to do it this way, but that's totally your call. Stronger number skills may not require this action, all right? Stronger numeracy skills. I'm going to rewrite this cube root of 9 as the cube root of 3 squared. Now, if I want to take the cube root, I need to have a perfect cube in my denominator. So I need to multiply by 1, represented as the cube root of 3 to the first power over the cube root of 3 to the first power. All right? Now, when I do this, this is going to give me a denominator of 9 times 3 of 27, 3 to the third. All right? I'm going to write this back again as 9. I'm going to write that as the cube root of 27. Now, when we do that, this tells us that the cube root of 1 over 9 is equal to the cube root of 3 divided by 3. All right, that's a lot of 3's in that exercise, so I apologize. Maybe I should have picked a different number. But we had 3 squared here, and we needed to multiply by another 3 to get a perfect cube, to get 3 to the third power. The cube root of 3 squared times the cube root of 3 to the 1 makes the cube root of 3 cubed, which is just 3. All right, that's how our denominator is going to work. This is a little bit challenging. Take some time and look at that, digest that, process that. In the denominator, in our fourth example here, we've got a variable in the denominator. So we've done some work with just arithmetic, we've done some work with algebra, and now we're going to wrap this up with cube roots with variables. All right, so this gets a little bit tricky. We're going to have the cube root of the numerator over the cube root of the denominator. Now this is a little bit interesting process. There are a couple ways you can go about this. There are easy ways, there are hard ways, there are smart ways. I'm going to go about this the smart way. I like to consider myself fairly intelligent. And so I want to be efficient here, and I want to save us a little bit of time and maybe a little bit of heartache and a little bit of headache. Numerator, we can't simplify. We're just going to leave that as is. But my denominator, I'm going to be smart about what I multiply by. All right, so I'm both numerator and denominator. I'm going to multiply by 1, represented as this, a special quantity over itself. Now, in order to make 5 into a perfect cube, I need to multiply by 5 squared. 5 times 25 makes 125, and that will make a perfect cube. That's 5 to the third power. Over here, I've got x squared. I just need to multiply by another x to make x cubed. All right, so I'm being a little bit strategic and intentional about the numbers that I pick here. I'm not just going to multiply by 5x squared times 5x squared. You could do that, but then you're going to make more work for yourself. All right, so 25x over 25x. So here's the cube root of 2 times the cube root of 25x. That makes the cube root of 50x that cannot be simplified. 2 times 5 times 5 times x. There's no perfect cubes in there. But down here, I've got the cube root of 125x to the third. Both 125 and x cubed are perfect cubes. I will write that as the cube root of 50x over 5x's. Holy smokes. Process that, understand it, and ask questions if necessary.